Thank you so much. Deputy Vice Chancellor, Dean, faculty, and students, thank you so much for coming today. It's really an honor to present to you all. Actually, Dr. Miller and I have been traveling right now for about 3.5 weeks in Africa. We spent about 2.5 weeks speaking in South Africa. We spoke at the University of Cape Town, Northwest University of Potchefstroom, another university called Academia, and then we've now been in Kenya here for about 4 or 5 days, and we actually fly home tomorrow, so we're almost done with this very long trip. This is actually day 37 out of 39 for me that I've been traveling away from home. But it's really a pleasure and an honor to be with you all today, and we're going to talk about the topic of origins. Where did things come from? And I know that there are many different perspectives on origins. There are people who come from a more atheistic perspective, where they think that everything evolved or just kind of arose through blind, mechanistic, even chance-based processes. There are other people who come from a faith kind of tradition, and there are many faith traditions out there who believe that life in the universe were ultimately created by God. I personally think it's very important to sort of just be upfront about where you're coming from. So I personally am a Christian, but today, and so I do believe the universe was created by God. However, today we're going to discuss this topic from the standpoint of science. We're not going to be discussing it from the standpoint of religion, and we're going to be talking about the idea of intelligent design. So I'm going to give you guys much more of a thorough background and introduction to intelligent design throughout the course of this lecture. But very, very briefly, just for the moment, intelligent design is the idea that life in the universe did not come about by purely blind physical mechanisms. Thank you. Did not come about by purely blind physical chance-based mechanisms. But there's actually an intelligent mind, a person, an intelligent being that designed the universe and designed the life that we see on this planet. And intelligent design does not come from any particular religious perspective. There are people of many different faith traditions, Christians, Jews, Muslims, people of many different views who we work with in the intelligent design community who find that the evidence for intelligent design is very compelling. So the way that we're going to approach this topic today is through science. And we're going to ask the question, is there scientific evidence that there is intelligent design behind life in the universe? Of course, you can take a faith tradition and say, well, yes, my religion teaches that life in the universe was designed, and that's fine. There's nothing wrong with that. But we're going to ask the question today, is there actually scientific evidence that life and the universe were designed? So first, let's define this idea of intelligent design. So intelligent design is a scientific theory which says that many features of nature are best explained by an intelligent cause rather than, for example, an undirected cause like natural selection. And the reason for this is because in our experience, what we see in these features of nature is information and complexity, which in our experience comes from intelligence. So we would say that intelligent design is the best explanation for many features that we see in life in the universe, because in our experience, intelligence is the cause of their informational properties. So what's interesting is that we constantly recognize design in the world around us. In our everyday life, we are constantly making what we call design inferences, where we recognize that things were designed. So I don't know if any of you have ever been to Disneyland. I actually grew up in Los Angeles, so every once in a while my grandmother would take me to Disneyland, and as you would walk up to the front gate, you would see these plants that had been carved into the shape of Mickey and Minnie Mouse. And when you see these plants, you immediately realize these plants did not grow into that shape through a natural process. No plant will grow into this shape naturally. These plants were carved into this shape for a purpose by an intelligent mind, an intelligent being. So we sort of instinctively recognize when things were designed without even realizing it. I'll give you guys a lot more examples of this as we go through this talk. So what is a design inference? A design inference is when you look at something and you say, that didn't come about by chance, or that did not happen by purely physical causes. Instead you say, this thing that I'm looking at was designed by an intelligent agent. It did not come about by strictly natural mechanisms. So what we like to ask in the intelligent design community is, what is the reasoning by which we use to detect design? What is the reasoning that we use when we say that this thing was designed and we make a design inference? So how many of you guys have ever played the game of Scrabble? Anybody ever played Scrabble in here? I'm sure some of you played Scrabble. My mother loves to play Scrabble. Whenever I go home to visit my family in Los Angeles, one of the first things my mom likes to do is to play Scrabble. So if you take a bag of Scrabble tiles and you pour that bag on the floor, what are you going to get? You're going to just get a random jumble of letters, right? It's going to basically be gibberish. It's not going to mean anything. So the tiles will be arranged randomly. There's no words, there's no meaning, there's no message, there's no information, okay? But now, of course, after you start playing the game, you might see that you're bored with something like this. And you'll see that there are words that have been arranged in a meaningful pattern. So what has changed from the first situation where we just have a random batch of letters that have been strewn all over the floor versus this arrangement where we have order and complexity and information? Well, now, what has changed is we have words, meaning, and information. And the question that we need to ask is, how did that information get there, and where does this information come from? Where does new information arise? So when we talk about intelligent design, information is sort of the fundamental principle, because in our experience, new information, new language, new codes come from intelligent agents. It comes from mind. And one of the common objections that we will get from folks when we talk about this is, well, you guys are not talking about science. This is not actually doing science. But what I'd like to point out is that there are actually a variety of scientific fields that are already using intelligent design-based reasoning. So for example, this is sort of just a hypothetical example. I'm kind of a sci-fi fanatic, but there's this old sci-fi movie called 2001: A Space Odyssey. And in this movie, there's sort of this Planet of the Apes where this strange obelisk-type structure appears. And the question that's being asked in this movie is, where did it come from? How did it get there? Or is this perhaps just a natural geological structure that grows out of the ground like a geological crystal? Or maybe do these apes just build these structures out of some instinct? Or maybe it was put there by some intelligent being for a purpose, to get people's attention, to try to accomplish some purpose. So how did it get there? So this points to what intelligent design is trying to help us do. It's trying to help us to tell the difference between things that on the one hand were designed for a purpose, and on the other hand, things that came about by purely natural, law-based and chance-based mechanisms. So we're trying to discriminate between, on the one hand, things that were designed by an intelligence, and on the other hand, things that came about by purely natural causes and did not have any design. And there are, again, as I said, there are a number of different scientific fields which are already using intelligent design type reasoning to tell the difference between things that were designed and things that came about naturally. So for example, in the US, sometimes when we go hiking, we find these things called arrowheads. Arrowheads obviously are the tip of a spear that has been, it's a rock that has been taken by a person. Native Americans would frequently take rocks and they would carve these stones into a shape, and then you would put them on the end of the spear, and then you would shoot a bow and arrow and use it to hunt and be able to get food. So when we find these arrowheads, we can immediately say, this is not just a rock that was carved into, that just has this shape due to random geological processes or normal geological forces. This is actually a rock that was carved into a shape for a purpose. So we can immediately recognize that it was designed. In fact, archaeologists will very frequently make design inferences. They will find a rock and they will say, this rock did not just come about in shape through natural processes. This rock was carved into a shape for a purpose. It was intelligently designed. Another field that uses intelligent design reasoning is forensic science. I don't know if any of you watch the TV show CSI, but in this show, what happens is they will find a dead body, and then they ask the question, how did this person die? Did this person die due to natural causes? Maybe a heart attack, maybe some other disease. Or was this person's death caused by intelligent causes, otherwise known as what? Murder, right? So these are actually very important questions that our legal system has to address. Anytime that we say, we put a person on trial for committing a crime, and we say, this person here is responsible for killing this person there, then we are actually making a design inference. We're saying that this death did not come about naturally. It came about due to a person who intelligently planned and caused that death to happen. So these are very important questions that we have to answer and address in our society. So what we in the intelligent design research community like to do is we like to say, look, if we can detect design in these other scientific fields, how about in biology, where we find that all of life is fundamentally based upon a language-based code? If in our experience, language-based codes always come from intelligence, can we use that principle to say that there are aspects of biology that were intelligently designed? So again, that's what we're trying to ask the question. Can we find evidence for design in nature? Another field that uses intelligent design reasoning is the search for extraterrestrial intelligence. I don't know if any of you have seen this old movie from the 90s, Contact, but it's about this group of scientists that are trying to detect design through a large array of radio telescopes that are scanning the skies for radio signals coming from outer space, hoping to find one that maybe was designed and sent by an intelligent alien civilization. I know aliens came up already a little bit. I have a feeling we're probably going to talk about it more as the day goes on. In fact, every Q&A session we've had so far here in Kenya, we've been talking about the question of aliens. So I'm sure we'll get into that more. But for now, let's talk about this project called the Search for Extraterrestrial Intelligence. This is a real scientific project where they have these radio telescopes that are trying to tell the difference between radio signals that on the one hand just occur naturally. Maybe they're sent by quasars or pulsars or other stellar phenomena, or on the other hand, a radio signal that might have been sent by an intelligent alien civilization. Now, they actually have not detected any alien signals yet using this project, okay? But I think that the very fact that they are trying to detect design in radio signals sent from outer space, they're trying to ask, can we tell if one of these radio signals was intelligently designed? I think that is very significant because they're trying to use ID reasoning. We often call intelligent design ID, so I'll say ID sometimes. What they're trying to do is, again, they're trying to tell the difference between radio signals that maybe just occurred naturally and radio signals that were intelligently designed by some alien civilization. And the fact that they're trying to do this is very significant. It shows that you can use ID principles and ID reasoning to detect design in nature and use science to detect design. So again, how do we detect design? Well, it really comes down to finding information. And there's a famous information theorist named Henry Quasler who said that the creation of new information is habitually associated with conscious activity. What's he saying? When we see new information being generated, in our experience it always comes from a mind or a personal agent. But what is the precise type of information that we are talking about when we say that information comes from a mind? I know for many of you who are physics students or mathematics students or computer science majors, you have probably studied different ways of defining information. Shannon information, Kolmogorov complexity. Well, the way that we define information that is detectable because it is produced by an intelligent agent in the ID community is what we call complex and specified information. We're going to talk about that more as the talk goes on. But for the moment, this is a very nice quote from one of our colleagues at Discovery Institute named Dr. Stephen Meyer. And here's what he says. He says, our experience-based knowledge of information flow confirms that systems with large amounts of specified complexity, especially codes and languages, invariably originate from an intelligent source, from a mind or a personal agent. So what is Dr. Meyer saying here? Well, first of all, he's saying that when we find large amounts of specified complexity, then that is a good indicator that an intelligent agent was at work. And I know this is sort of a bit of a technical term here, so don't worry, we're going to unpack this term and I'm going to explain it before this talk is over. I think you guys have a good understanding of what this idea means. But he gives two examples of types of specified complexity, codes and languages. He says that they invariably originate from an intelligent source, from a mind or a personal agent. So what's interesting is, what do we find at the very heart of life? Do we find language-based codes in living organisms? We're going to talk about that, because if we do, then that would be a good clue that an intelligent agent designed life. So what do we mean when we use this term, complex and specified information? Well, first of all, something is complex if it is unlikely, okay? So if you see on the screen, let's say, this is just a hypothetical example, you're looking under a microscope and you see this series of zeros and ones in this microorganism, okay? So 0, 1, 0, 0, 0, 1, 0, 1's up, etc., etc. Now, the likelihood of you getting this exact sequence of zeros and ones is very unlikely, right? Let's say if you're flipping a coin, and for every heads you write down a 1, and for every tails you write down a 0. The likelihood of you getting this exact sequence of zeros and ones is very unlikely. So we're going to say that this is a complex sequence of numbers here. Now, is unlikelihood or complexity alone enough for us to say that something was designed? Can we say that something is designed simply because it is unlikely? The answer to that is no. For example, unlikely things can happen all the time, and we don't necessarily detect design. The odds of every one of you sitting in the exact seat that you're in today in this room is very, very low. But we're not going to say that there was some grand scheme or grand plan to make you sit exactly where you were sitting. Or take the example of playing a game of poker. I don't know if any of you guys play poker. I don't play a lot of poker, but I actually once won a $1,000 poker tournament because I got very lucky, actually. I'm not a very good poker player, but I got a very good string of cards, okay? But if I were to deal each of you out a 5-card hand of poker, the likelihood that every one of you would get the exact hand of cards that you get is very, very low, okay? So that just because you get a very unlikely hand of cards does not mean that therefore you're going to say, oh, the deck was stacked, this hand of cards was somehow intelligently planned. Because unlikely things happen all the time, and that doesn't necessarily mean it was designed. Even if you get a very good hand of cards, like say a royal flush, you're not going to necessarily say, oh, look, the deck was stacked. But now let's say that I deal every one of you out a 5-card hand of poker, and every one of you gets a royal flush, okay? And you keep getting royal flushes every single time I deal out the hand of cards. Now you're going to say, okay, there's something interesting going on here. There's a pattern coming up. It's not just a random shuffling of the cards that did this. I think the deck was stacked because I'm seeing a repeating pattern that keeps coming up over and over again. So going back to this example, this is actually not just a random sequence of zeros and ones. This is actually a sequence of zeros and ones. Well, actually, I'm just curious. I'm sure some of you guys are going to raise your hands. But how many of you do computer programming in this room? I'm sure some of you do, right? Computer science majors, yeah. So I had to write about 30,000 lines of Python code during my PhD at the University of Johannesburg. Oh, and then you asked, when did I finish? I finished it in 2020, actually. So I actually finished writing my PhD thesis the same week that they announced the lockdown for COVID in March of 2020. And it was really hectic. My wife and I had to fly back to the U.S. and give everything we owned away and basically, get home before all the borders closed. It was really crazy. But I did a lot of Python programming during my PhD, so much that my wife got me this t-shirt that said, I dream in Python, because all I could do was talk about Python programming. But it turns out that this is not a random sequence of zeros. The computer science majors know what I'm talking about. You can't stop thinking about how am I going to write this program. So this is not a random sequence of zeros and ones. This is actually binary code for the ASCII characters that spell out this sentence, okay? So this sentence says, biology is the study of complicated things that give the appearance of having been designed for a purpose. Biology is the study of complicated things that give the appearance of having been designed for a purpose. This is actually a quote from Richard Dawkins, the very famous atheist scientist and evolutionary biologist, who, by the way, is no friend or supporter of intelligent design. He thinks that, life was basically the result of natural selection and random mutation. But yet, even Richard Dawkins acknowledges that biology is the study of complicated things that give the appearance of having been designed for a purpose. He acknowledges that living things appear to be designed. Well, we in the IT community would say that perhaps the reason that things appear to be designed is because they really were designed. It's not just apparent design, it's real design. But this gets to how we detect design. We have something that is both unlikely, but then those zeros and ones that we saw, they also actually match a pattern. Namely, they encode this sentence in the English language that we can recognize. So we will say something is designed when it is both complex, meaning it is unlikely, and when it is also specified, meaning it matches some independent pattern. So in this case, we immediately recognize that this sentence was designed because it is an unlikely sequence of characters that also match the pattern we recognize from the English language. Let me give you guys another illustration of how to understand this idea of complex and specified information and how that helps us to detect design. We're going to use kind of a silly example. This is Billy Bob. Billy Bob was going on a tour of mountains of the United States, okay? So first Billy Bob comes to this mountain, okay? He says, this looks like a normally shaped mountain, okay? The likelihood of this mountain having a ridge right here, and a ridge there, and a ridge there, and a gully here, and a gully there, the likelihood of this mountain having the exact shape that it does is actually very, very low. So we would say it has a complex shape. But would we say that this mountain's shape was intelligently designed? No. We can easily explain the shape of this mountain through normal geological processes like wind and erosion and heating and cooling and freezing and thawing and so on. So he would say this looks like a normally shaped mountain. It has a shape that is unlikely or complex, but it's not specified to match some special pattern. Therefore, he's going to say the mountain's shape is natural. It was not intelligently designed. Some of you can maybe guess where we're going to go next, but now Billy Bob comes to this mountain, okay? This is Mount Rushmore in the U.S. I've actually never been there. It's on my bucket list. But now he goes to this mountain. Billy Bob says, okay, this mountain also has a very unlikely shape, yet it matches a known pattern. There's something special about this mountain, and that it matches a pattern, namely the shapes of the faces of 4 famous presidents. So now he sees a specific pattern plus complexity. He says the shape of this mountain was intelligently designed. And so then if he were to go to the back side of the mountain, he would see this. We just used information to detect design. So this is not what the back side of Mount Rushmore actually looks like. This is a joke. But we did actually just use the idea of complex and specified information to detect design, okay? So we're now using information to detect design. And detecting design is very important. Design inferences can actually save your life. So let's say if you're driving down the road and you see a giant white splotch of paint on the road. And it just looks like maybe a can of paint fell off a truck. It's a very unlikely shape. It's very complex, but it has no pattern. So you see this paint all over the ground, you're going to think, oh, a can of paint fell off a truck, there's nothing for me to see here, and you just keep on driving, okay? But now you come across this paint on the ground, okay? This paint also has a very unlikely shape, but in this case, it matches letters and words in the English language that are giving you a very important warning, namely to stop because there's a railroad crossing. So when we make design inferences, they literally can save our lives. We make design inferences all the time without even thinking about it, using this sort of reasoning of complex and specified information, finding something that's both unlikely and also matches a pattern, and this actually can help save our lives, and we don't even realize that this is the way we're reasoning. So I want you guys to now try a few examples of detecting design. Okay, I'm sorry, but this is going to require some audience participation, and I know we're all kind of tired, it's early in the morning, but we'll get the blood flowing here. So first of all, this example. Who thinks this is design and who thinks this is natural? Raise your hand if you think this was designed. Okay, raise your hand if you think that these are natural. Okay, I would agree with you. Okay, well, I would agree with those who said that it was designed. Okay, these are the famous head carvings from Easter Islands. And in this island, these rocks, these carvings are actually made out of the same basaltic rock that makes up the mass of the island. But there's something special about these rocks, and that they are carved in the shapes of heads, and so we can clearly see that they are both an unlikely shape that matches a known pattern, and therefore we say that they were designed. And they match the shape of the head pretty closely, so they're very, very highly specified. But what about this one? Who would say that this was designed? Who would say this is natural? Okay, again, I would agree with you. And I'll just go through these quickly so we can keep moving. The reason why I would say this is natural is because it is unlikely, it's very unlikely to get this exact sort of configuration, but it also doesn't match actually pattern. There's no pattern to be found here. It just looks like randomly strewn clods of dirt. So there's no complex and specified information here. What about this one? Who would say this one is designed? Who would say this one is natural? This one's a bit tricky, you guys, and actually we have a very nice lighting and projector here, so you can see this one really well. Sometimes in darker rooms, or in lights, there's more light in the room, it's harder to see, but you can see that there are features on this hand that show that it really does very precisely match the shape of a hand. So this is both unlikely, it's complex, but it's also very closely specified to match the shape of a human hand. And this is actually a sculpture that was made in the Atacama Desert of Chile. What about this one? Who would say this one is designed? Who would say this one is natural? So if you said that it was natural, my initial inclination is I would agree with you, because it's not at all difficult to look up at the sky and see a cloud that maybe sort of vaguely matches the shape of a face or an animal or something like that, but it's not very highly specified. It's not very unlikely to get this, and there's not a lot of specification here. It's not like it has a very precise match to the shape of a face, but certainly, it sort of vaguely matches it. Now, I always said this was a natural photograph, and then one day a student pointed out to me, this is actually photoshopped. If you look right there, you can see some weird lines in the photo. So this actually is designed, but if you said it was natural, we'll go with that. I think your instincts are pretty much right. What about this one? Who would say this is designed? Who would say this is natural? Okay, yeah, it's a tricky one. Some of these can be a little bit challenging, and they show that detecting design is not always easy. And we have to be very careful. We don't want to say that something was designed when it really wasn't. If you said this was natural, I do agree with you, and I think you are correct. This is a snowflake, and even though it has a very highly specified shape, that shape is determined by natural chemical forces that order atoms into basically crystal structures through the laws of geometric packing and bonding, okay? So if you have basically a pool of water and you cool it below the freezing temperature, you are 100% guaranteed you are going to form water crystals, okay? So this is a normal natural chemical process, so that means it's actually not unlikely. There's not complexity here. Even though it's very highly ordered, it's very highly specified, it's not actually an unlikely event. It's very likely to occur given the right set of natural and chemical conditions. What about this one? Who would say this one is designed? Who would say this one is natural? Again, this is tricky, guys. So this is actually also a crystal. This is a geological crystal in a rock. And again, given the right conditions, given the right, say, magma composition, and given the right conditions of cooling that magma, you are guaranteed to form crystals out, and which will then crystallize into a rock, and that's what's happened here. But if you look closely, you can see things that are telltale signs. Where there's more going on here. You see these other crystal bits here that did not crystallize into the shape. You can see other crystal components, and so I would say this is a natural structure. So going back to aliens, who would say, what would you guys think of this one? This is the famous face on Mars. Is this natural? Who thinks it's natural? I guess this is a test of whether you believe in aliens. Is this natural, or who thinks it was designed? Okay, well, nobody wants to admit to it, I guess, if they think it was made by aliens. Look, my personal view is that this is natural. This is just a hill that's found on the surface of the planet Mars. It does not have a very tight specification to the shape of a face. It's not very unlikely to get the shape of a face. And in fact, I think if you were to look at this little hill in a different lighting setup, it probably wouldn't even necessarily look like a face. So this is surely something I would say is natural. But look, the basic logic that we're using here is as follows. We see an intelligent design theorist observes that certain types of information, namely complex and specified information, which we also call CSI, by the way, an intelligent design theorist will observe that mind is the cause of certain types of information, and then she will go out and she will find that in natural objects, she finds that same kind of information, which in her experience always comes from intelligence. So she infers that the mind was at work in generating that object. Okay, so let's keep moving on here. Just a little bit more about what intelligent design is, and then we're going to dive into the scientific evidence. So intelligent design is not a theory that specifies the identity of the designer or describes the nature of the supernatural. All we're inferring is an intelligent cause. And we're not getting into questions about who the designer is. And that's more of a religious question, and there are a variety of different ways you can explore that question of who the designer is through various religious arguments or religious topics. But idea tries to remain strictly as a science, and so it doesn't get into the question of who the designer is. ID is also not merely a negative argument against evolution. ID acknowledges that there are some features of nature that are best explained by evolutionary mechanisms. We're not going to say that everything has to be designed. There are some features that we find that are best explained by natural evolutionary mechanisms. But we would also say that there are some things that are not very well explained by natural evolutionary mechanisms. And our case for design does not simply require us to refute evolution. We have to also find positive evidence for design. Evidence against one scientific theory is not therefore in and of itself evidence for another scientific theory. You need to have a positive argument in order to say that something was designed. And so, again, as I said earlier, when we define intelligent design, we infer design, we detect design by finding in nature the kind of information and complexity which in our experience only comes from an intelligent agent. So this is a positive argument based upon finding in nature the kinds of information, the kinds of complexity, which from our experience always come from intelligence. ID is also not a theory about the age of the earth. I personally do accept, billions of year old age of the earth. I don't have any problem with that. But it's not getting into the question of the age of the earth. And it's also not a theological or religious theory about how Genesis fits with science. Again, nothing wrong if you want to try to fit science with a holy book or science with the scriptures. I have no problem with that. That's a very interesting and fascinating topic, and it's a great thing to do. But ID is not getting into that question. All ID is saying is, can we look at the evidence from nature alone and see that there is evidence for a designer and a creator behind life and the universe? So what this means is that ID is different from creationism. Creationism always explicitly appeals to a supernatural or divine creator. Creationism almost always also bases its claims upon the Bible or some other religious text. In contrast, intelligent design only appeals to an intelligent cause, and it's based upon the scientific data. It's based strictly upon what we can learn from the scientific evidence. It's not grounding its arguments in the Bible or some holy book. It's simply grounding its arguments in what we see from nature and the world around us. Now, ID is not against the Bible in any way, but again, it doesn't ask how we can harmonize science with the Bible or other holy books. It's simply not getting into those questions. So ID is different from creationism. It's not creationism in a cheap tuxedo, as it is sometimes been called. So what is ID? ID is a scientific theory which uses the scientific method to show that we can use information to detect design in nature. It's also supported by credible scientists. It's supported by a growing research program which has published many peer-reviewed scientific papers, and it's also a positive argument backed by much scientific evidence. So you can disagree with the conclusions of intelligent design, but I don't think the argument that I've used today for how we detect design, I'm not appealing to the Bible, I'm not appealing to religion, I'm appealing to what we see in nature. It's based upon science. So let's now put intelligent design to the test and ask, what is some of the scientific evidence for intelligent design? And let's go back to this quote that I mentioned earlier from Dr. Stephen Meyer. It says, our experience-based knowledge of information flow confirms that systems with large amounts of specified complexity, especially codes and languages, invariably originate from an intelligent source for a mind or a personal agent. Again, what is he saying here? When we find things like specified complexity or complex and specified information, when we find things like codes and languages, in our experience, those things always and only come from an intelligent agent. So let's now talk about the field of biochemistry, and if we see evidence for design in biochemistry. And we're going to make a testable prediction that biology will be full of information-rich structures, including language-based codes and machines that contain high, complex, and specified information, also called CSI. So if we think back to how science has progressed over the last 150 years, and we think about what Darwin knew when Darwin came up with his theory of evolution. In Darwin's day, we did not have a very good understanding of the cell. The cell was thought of basically as a very simple glob of protoplasm. This wasn't Darwin's fault. This was just the knowledge that biologists had at this time in the 1800s when Darwin's theory was first constructed. And today, however, we know far more about the cell. We know far more about biology. We know that the cell is not just a simple blob of protoplasm. What we see in the cell actually is like a miniature city or a miniature factory, complete with energy production units, waste disposal units, recycling machines, machines that are involved in transporting vital parts from one end of the cell to the other. We have components that are used to break down food and engage in metabolism. We have smart barriers which help to prevent harmful substances from entering the cell and allow helpful substances to come into the cell. We have central processing units. We have all kinds of complex, what we call molecular machines that are running around inside of your cells performing all kinds of vital cellular functions. So the basic complexity of the cell is mind-boggling. In fact, if you were to take the most advanced technology that we have today, iPhone, some other technology, that does not hold a candle to the simplest bacterial life form, okay? The simplest life form is far more complex than any technology that has ever been made by human beings. And so the complexity of the cell, we still don't fully understand how the cell works. In fact, this diagram shows the minimal genome of basically the smallest and most simple bacterium that we've discovered so far, okay? And there are still hundreds of genes that we know are necessary for this bacteria to be able to survive and live. And we don't even know what some of those genes are doing, but we know that hundreds of genes are required. We don't fully understand how it operates, how it works. We're still trying to understand the secrets of the cell. We learned a lot, but there's still much that we don't fully understand. So the basic complexity of the cell goes beyond any technology ever made by humans. So as we talk about the basic design of biology, we're going to look at 3 layers of design. We're going to look at encoded information in our DNA. We're going to talk about the information processing ability of the cell. And finally, we're going to talk about the product of that information processing, namely protein-based molecular machines. And as we talk about this, a key question we're going to ask is, where does new information come from? So let's talk about encoded information. I know that many of you have studied science, so probably some of this is going to be very, very familiar to you, but I want to give us a very, very basic molecular biology review here to help us understand some of the basic complexity of the cell and how the cell works. So if we just exclude red blood cells, every cell in your body has 46 chromosomes, basically the full complement of all of your DNA that's necessary to build your body and build all the proteins in your body, okay? And how is information stored in your DNA? Well, information is stored in your DNA using 4 molecules called nucleotide bases. Their names are adenine, cytosine, thymine, and guanine. They're represented here with the letters A, T, C, and G. And DNA is a very beautiful molecule. In fact, it's in your cells, in its normal state, it's wound up and compacted very tightly into these structures called chromosomes. But if you were to unwind all the DNA in one cell, it would come out to about 2 meters in length. So if you multiply that by, trillions of cells in your body, it would be, trillions of meters basically in size. Very, very huge amount of DNA is compacted into your body. But if we unwind that DNA, what we would see is this sort of beautiful spiral-shaped molecule. We call it the double helix, with these 2 different strands of this phosphate, deoxyribophosphate group that is twisted around. And along this backbone of the DNA molecule, you would see things that look kind of like rungs of a ladder, that look kind of like stairs along a spiral staircase. And those are represented in this diagram with the letters A, T, C, and G. And what's interesting is that it is the ordering of these nucleotide bases, these rungs of a ladder along the backbone of your DNA, that determines the amino acid sequence of every one of your proteins. So we have to have these nucleotide bases in just the right ordering, or your bodies will not be able to produce the proteins properly that you need to survive. In fact, when you have one of these nucleotide bases in the wrong order, we call it a mutation. And mutations frequently cause severe illness, sickness, or death. And so you have to have these nucleotide bases in the right order in order to get the amino acids and your proteins in the right order so that you can live and survive properly. So one of the most interesting discoveries for me is that this is basically information, and there is no physical or chemical law that dictates the ordering of the nucleotide bases. I want you guys to appreciate this point. There is no physical or chemical law which says that these nucleotide bases have to be in any particular order in your DNA. So what is putting the nucleotide bases in just the right order in the DNA of living organisms so that they can produce their proteins and live the way they're supposed to live? Well, that's a very interesting question. And the fact that this information, these nucleotide bases are in the right order represents information. We have a very unlikely sequence of these nucleotide bases that matches the exact pattern that you need to produce functional proteins. So that would mean that it is complex and specified information. And it's not just people from the intelligent design community who would say that there's information in our DNA. This is a quote from a paper in the journal Nature, one of the top journals in the scientific community, called The Digital Code of DNA, by two leading scientists. It says, DNA can accommodate almost any sequence of base pairs, any combination of the bases adenine, cytosine, guanine, and thymine, and hence any digital message or information. So it's the ability of DNA to carry all these nucleotides in any particular order that means that it is carrying information. So what are the implications of this? Well, again, what is a protein? Proteins are basically the molecules that perform many of the vital functions inside of your cell. RNA and other molecules also perform vital functions, but proteins are sort of known as the workhorse molecules of the cell. They perform many of your body structures, and they perform many of the vital functions in your cells. And proteins are basically long chains of amino acids that are folded up into a particular shape to form a particular function. So how does the information in DNA get converted into a protein? Well, it's a complex process called transcription and translation. I'm not going to go into too much detail about that right now, but suffice to say...
How are we going? We just...
Testing. Oh, we're back. Okay, good. We're good. Yeah. Okay, we're good. So, in your DNA, again, you have these nucleotide bases, and it is the precise ordering of these nucleotide bases that determines the ordering of the amino acids in your proteins. So what happens is, through a process of transcription and translation, we'll talk more about this in just a minute, you convert the information in your DNA into a sequence of amino acids, and this would be sort of like an unfolded protein, an unfolded amino acid chain, and these amino acid chains then fold up into a very complex shape, which would be a protein, to perform some function inside of your cells. And again, you have to have the nucleotide bases in just the right order in order to get the amino acids in the right order so that you can then have a protein that can perform its functions. So one of the questions that we ask in the ID research community is just how precisely ordered do these nucleotide bases, do these amino acids have to be in order to generate functional proteins? So Douglas Axe is a Caltech PhD protein scientist who has asked this question: how common or rare are functional sequences of amino acids, i.e. proteins, among all the possible combinations of amino acids, okay? So there are, typically we would say, there are 20 amino acids that are used by living organisms. So let's say you have a very short protein that's only 10 amino acids long, okay? The likelihood of getting a precise sequence of amino acids in that protein would be 1 in 10 times 1 in 20 times 1 in 20 times 1 in 20, basically 10 times. So it would be 1 in 20 to the 10th power. And so what we can see is that even a very short protein can have a huge possible number of amino acid sequences. So what he's basically asking is, are proteins CSI-rich features? Do they have a very unlikely sequence that then has to be tightly specified to match a very particular pattern so that you can get a functional protein? And here's that research where basically he would mutate a particular enzyme, and he would find that as you go through sequence space, as you basically mutate a protein or an enzyme and change its amino acid sequence, most amino acid sequences that you look at do not give you a functional protein. It's only when you get to a very precise amino acid sequence that suddenly you will get a functional protein. So what he's found is that the likelihood of a random sequence of amino acids giving us a functional protein that's about 150 amino acids in length, looking at a particular enzyme in bacteria called beta-lactamase, so a fairly typical enzyme. He found that the likelihood of you being able to get a functional protein fold is 1 in 10 to the 77 sequences. So only 1 in every 10 to the 77 sequences will give you a functional protein fold. So what this means is that many amino acids have to be just right in order to get you a functional protein or a functional protein fold. So this is what we would call complex and specified information in our proteins, okay? We have a very unlikely sequence of amino acids that matches a very precise pattern that has to be there in order to give you a functional protein. And this tells us that there is functional, complex, and specified information in our DNA because remember, it's the order of those nucleotide bases in the DNA that dictates the ordering of the amino acids in proteins. So it shows that there is high levels of complex and specified information in our DNA. So now we can ask the question, can functional proteins evolve? What is the likelihood of a functional protein evolving? So what Dr. Axe's research shows is that basically you will get a functional fold for every 10 to the 77 amino acid sequences. Only 1 in 10 to the 77 will give you a functional protein fold. Now, there's a problem here for the evolutionary process, and that's this. There have only been about 10 to the 40th organisms that have lived over the entire history of life on Earth, okay? So if we were to make this incredibly generous assumption for evolution, that basically every single living organism that has ever lived was somehow magically granted a random sequence of about 150 amino acids in hopes that it would be able to give you a functional protein. If we were to do that, we would still be short by about 10 to the 37th trials just to get a single functional protein over the entire history of life on Earth. What this tells you, and I know you guys are all studying technical degrees here, so I don't need to explain the math to you guys. You can see that the denominator is far greater than the numerator. There's a problem here, okay? So we do not have enough opportunities or trials over the entire history of life for evolutionary mechanisms to produce the high level of complex and specified information that we observe in many proteins. There is just not enough opportunities to produce this kind of complexity. So I think that what we can see is that there is high CSI in living systems. Now, let's get back to DNA, okay? It turns out that the way that our cells will use the information in DNA is a lot like the way computers process information. And to explain why, I want to use an example of a DVD, okay? A DNA molecule by itself is basically useless. It's not going to do anything. It's just sitting there. It has a lot of information in it, but it's not actually going to do anything. It's kind of like having just a DVD by itself, okay? So a DVD on its own is useless. Maybe you could use a DVD as a frisbee, or you could use it as a coaster, or something like that. But a DVD on itself, there's no way for you to get the information off that DVD. So in order to use a DVD, you need a machine which can read the DVD, process that information on the DVD, and give you some kind of useful output, the movie that you want to watch, okay? In a very, very similar way, DNA on its own is also useless. The DNA molecule is not going to do anything. Yes, there's information in it, but it's not going to be able to somehow make that information useful to you. In order to use the information in the DNA, your cells literally have what we call molecular machines. And these are microscopic machines that are capable of reading the information in the DNA. This molecular machine is called RNA polymerase, and this molecular machine is called the ribosome. These molecular machines can read the information in your DNA, process that information through a computer-like sort of form of information processing, and then give you the output that you need, namely functional proteins. These functional proteins then build molecular machines. Those molecular machines then build tissues and organs which make up your body, okay? But it starts with being able to use that information in the DNA, and it's used through a system of computer-like information processing. So why do we call it computer-like information processing? Well, because there are literally computer-like commands and codes inside your DNA. That information in your DNA literally contains commands and instructions that are interpreted by the machinery of the cell, much like how a computer will interpret a software program. So again, our DNA literally contains commands and instructions written in a biochemical language, much like software or computer code, and our cells are processing that information in much the same way that computers process information. And again, it's not just people in the IT community who are saying this. Leading biologists have said much the same thing. Francis Collins, who until just recently was head of the National Institutes of Health in the USA, he was also the head of the Human Genome Project, okay? He says that DNA is something like the hard drive on a computer containing programming. Another leading biologist named Craig Venter, who was also very involved with the Human Genome Project, he says life is a DNA software system and is the software of life containing digital information or digital code. In Seattle, where I live in the United States, one of the most famous people from Seattle would be Bill Gates. How many of you guys have heard of Bill Gates, right? He's the founder of Microsoft. Those of us who use Windows computers, this is supposed to be a blue screen of death, by the way, it's not. But, we love Windows computers, we hate Windows computers, but Bill Gates basically invented Windows. And Bill Gates has said that DNA is like a computer program, but far, far more advanced than any we've ever created. Even Richard Dawkins, again, no friend of intelligent design. In fact, to my knowledge, none of these scientists I'm quoting right now are supportive of intelligent design, yet they recognize the computer-like similarities of DNA and the information processing that goes on in the cell. Dawkins says the machine code of the genes is uncannily computer-like. Apart from differences in jargon, the pages of a molecular biology journal might be interchanged with those of a computer engineering journal. So these scientists recognize what's going on in our DNA, what's going on in our cells, looks like computer programming. But then what is the product of this process of computer-like information processing that goes on in the cells? What we're actually making are molecular machines. There are actually all kinds of molecular machines in your cells that are running around performing all kinds of important functions. Dr. Miller is going to talk to you guys more about this molecular machine. This is called ATP synthase. This molecular machine is actually Dad Norley's favorite. This is the kinesin molecule. I think you might have even named your dog Kinesin. This is a little molecular machine that literally has two legs, and it walks along these microtubules in the cell to transport cellular parts from one end of the cell to the other to get them where they need to go. But living cells are full of all kinds of different molecular machines and encoded information. Now, there's something special about these molecular machines, and that is that they pose a great challenge to Darwinian evolution. Now, of course, Darwin in his day didn't know about these molecular machines because they were not discovered until just the last maybe 30 or 40 years as we developed the technology to study what is going on inside of cells. But Darwin understood how evolution worked, and he put forth a very nice challenge and a way to test his theory. And this is what Darwin said. He said, if it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous successive slight modifications, my theory would absolutely break down. So what is Darwin saying here? He's saying that when we look at a living structure, a structure of a biological organism, everything in biology has to be able to evolve by what Darwin calls one little tiny step at a time. Numerous successive slight modifications, where each step of some evolutionary pathway is not just functional, but it gives you some advantage in helping you to become better able to survive and reproduce. That way you leave more offspring, and that way the species will evolve in your direction. But what Darwin is saying is that everything has to be able to evolve by numerous successive slight modifications, one tiny little step at a time. So there's a problem though. There are some structures that we see in living organisms where you have to have many parts present all at once or they won't function. And we call these irreducible complexity. They're irreducibly complex because if you remove a part or you change a part, then they stop working. So you can't remove the parts, you can't reduce the complexity, so they are what we would call irreducibly complex. If you take a part away, then they stop functioning. The problem that these irreducibly complex structures pose for the evolutionary process is that they can't evolve one tiny little step at a time. Either all the complexity, or at least a certain minimal set of parts, has to be there all at once and they work, or you're missing a component and it doesn't work, and there's no reason for natural selection to preserve the structure and help it to be built up in the organism. So again, these structures need a certain minimal core set of parts to be present, or they don't work. So you can't build them up one step at a time, because they don't work until you get a certain threshold level of parts and complexity that is present. It's kind of like a bicycle. I like to use this example. If you're riding a bicycle, there's certain parts of a bicycle that have to be there for the bike to be able to work. You have to have at least 2 wheels. You need to have a frame. You need to have a steering mechanism. You need to have some kind of motor mechanism. So there's certain minimal parts that have to be present for a bike to work. So a bike would be what we call irreducibly complex. Now, you might be able to ride a bike without a seat, right? So sometimes you might have some parts that you don't need in order to have that function of the system. But the fact remains you have this sort of irreducible core, this core of parts that have to be present, and this represents the irreducibly complex core parts that are necessary for a system to work. And we can see that many biological machines are irreducibly complex. This is a molecular machine called the bacterial flagellum. It basically functions like a propeller or an outboard motor on the back of bacteria to help bacteria to swim around and find food. And these bacterial flagella are really amazing. They actually are self-assembled and repaired rotary engines. And many of you guys are car fanatics, and you know about the Mazda RX-7 or RX-8. It uses a rotary engine, very similar design to what we see in the bacterial flagellum. And in fact, bacterial flagellum has a variety of parts that look like components from human design technology. It has a rotor, it has a stator, it has a U-joint, it has bearings, it has a propeller. So this molecular machine looks like something that was designed. It's driven by the flow of protons, although the exact mechanism is not fully understood. It can spin in 2 directions, forward and reverse. It can stop fractions in a quarter of a turn, which is pretty impressive when you realize that they typically operate at about 18,000 RPM, although they've been clocked at over 100,000 RPM. And what's really interesting about this molecular machine is there are over 50 genes that produce over 30 different structural parts of the bacterial flagellum. And biologists have done genetic knockout experiments on the flagellum, which has shown that they need about 35 protein parts or genes to be able to function. So what that means is that by definition, the bacterial flagellum is irreducibly complex. You have to have a certain core minimum number of parts present, or the bacterial flagellum will not spin around and help bacteria swim around to be able to find food. So the bacterial flagellum is a good example of irreducible complexity. So I would say that life is information rich, and we fulfill our prediction. In living organisms, we have found encoded information in the DNA. We found this information processing ability of the cell. We found that information is very high levels of complex and specified information. We also find in the cells machine-like structures. The product of information processing is protein-based molecular machines. But where in our experience do these kinds of things come from? Language-based code, computer-like information processing, and machine-like structures. In all of our experience, these have only one known source, and that is intelligence, okay? Language-based code that we see in our DNA, computer-like information processing that's going on in the cell, and these machine-like structures, these molecular machines made of proteins that are running around your cells, performing all these vital functions. In all of our experience, these kinds of things only come from intelligence. So we think this is very powerful evidence for intelligent design. So I think it's because of this that we see quotes like this. This is a quote from Francis Crick, who was a biologist who was co-awarded the Nobel Prize for helping to discover the structure of DNA. And he said that biologists must constantly keep in mind that what they see was not designed, but rather evolved. Now, Francis Crick was an atheist and an evolutionary scientist, but he has to keep reminding himself that life was not designed because it actually looks like it was designed. I find this to be very interesting. Again, Richard Dawkins says, Biology is the study of complicated things that give the appearance of having been designed for a purpose. And again, we would say the reason that things look designed is because they really were designed. Okay, so IV's prediction is confirmed. But it's important to understand that intelligent design is much more than just biology. We can also discuss design of the universe. Brian, you're not going to go into design of the universe, are you? Okay, so we'll look at this very quickly. And we're going to talk about how there's evidence for design in physics and cosmology. We're going to start with another testable prediction, which is that the universe itself will show fine-tuning for life, high CSI in the configuration of the laws and constants of the universe. So what do I mean when I use the phrase fine-tuning? Well, fine-tuning exists when we find that nature exhibits some unlikely property that matches a value or state that is necessary for life to exist. Okay, so fine-tuning is what we mean when we say nature exhibits some unlikely property that matches a precise value or state that is necessary for life to exist. Let me give you guys some examples of what we're talking about here. Let's say that you have in your home, in your bedroom, you have a universe creating machine. Okay, so you can go home, you can turn on your universe creating machine, and you can make universes. All right. So let's say that you want to make a universe where life can exist. Well, it turns out that in order to make a universe that would allow life to exist, you would have to have some of the very basic forces of physics set to very, very precise values. So you have these knobs on your universe-making machine that allow you to change some of the fundamental constants of the universe to change the various values of the strengths of these forces. So, for example, the strong nuclear force, the weak nuclear force, the electromagnetic force, the gravitational force, the cosmological constant, which is related to the expansion rate of the universe, or the speed of light. Each of these fundamental laws and constants of the universe have to be very, very precisely fine-tuned if you're going to have a universe where life can exist. So, for example, let's talk about the strong nuclear force, one of the forces that helps to hold the atom together. If you had a strong nuclear force that was just slightly stronger, you would have no hydrogen, which is an essential element for life, so life cannot exist. But if it was slightly weaker, you would have only hydrogen in the universe. You would not be able to make many of the complex molecules we need for life. The weak nuclear force, if it was just slightly stronger, you would not have enough helium to generate heavy elements in stars which are needed for life to exist. But if it was slightly weaker, then stars would burn out too quickly, and you would not be able to scatter the elements that life needs around the universe through supernova explosions. The electromagnetic force, if it was just slightly stronger or weaker, then you would not be able to form atomic bonds, you couldn't do chemistry, and therefore you could not make many of the molecules that you would need for life. And finally, the gravitational constant. If it was slightly stronger, then stars would burn too hot and too quickly to allow for life to exist. Or if it was a little bit weaker, then stars would never burn at all. You would never be able to have the energy that life needs, and heavy elements that life needs would also not be produced. So when we talk about the fine-tuning of the laws of nature, just how precisely fine-tuned do these physical laws need to be? Well, if we talk about the gravitational constant, in order for life to exist, physicists and cosmologists have determined that it has to be fine-tuned to within 1 part in 10 to the 35th power. The electromagnetic force versus the force of gravity has to be fine-tuned within 1 part in 10 to the 40th power. The cosmological constant, which again is related to the expansion rate of the universe, but is also necessary to be fine-tuned for life to exist. It has to be fine-tuned within 1 part in 10 to the 90th power. But I think one of the most extraordinary examples of fine-tuning have to do with why matter clumps into galaxies, okay? So if you think about, the way that matter could potentially be spread out around the universe, there are a lot of different ways that matter could be spread out. You could have matter spread so thinly that it never actually, one atom would never interact with another atom, and you would never be able to create things like galaxies or stars or planets. Or matter would be very, very clumped together very tightly, such that you would only have massive black holes in our universe, which again, either of those states, matter that is too thinly spread out, or matter that is clumped together in massive black holes, either state would not be a universe that would be friendly for life to exist in. But it turns out that there are 3 finely tuned parameters of the laws of nature which allow us to form galaxies galaxies. It's sort of like this in-between state. Matter's not too spread out, it's also not too dense, and therefore you can form things like galaxies and stars and planets. The first parameter is the mass density of the universe, which must be fine-tuned within 1 part in 10 to the 60th power. The second part is the expansion rate of the universe, which has to be fine-tuned to 1 part in 10 to the 55th power. But this last one kind of blows all of the other fine-tuning parameters away. This is the initial entropy, basically the initial disorder of the universe. It has to be fine-tuned to within 1 part in 10 raised to the power of 10 to the 123rd power, okay? So if you were to try to write out this number, 1 in 10 raised to the power of 10 to the 123rd, that would be 10 with 10 to the 123rd zeros after it. So if you tried to write that number out, you would start writing now, and you would die long before you even get a tiny fraction of the way there, okay? So we don't even have words to describe numbers that are this small or this big, depending on how you look at it. So what this means is the following. I think that it shows that great care was taken in the crafting of the universe and its physical laws and constants. And in fact, this has been recognized by leading scientists. This is a quote by Charles Towns, who was a Nobel Prize-winning physicist. He said, "Intelligent design, as one sees it from a scientific point of view, seems to be quite real. This is a very special universe. It's remarkable that it came out just this way. If the laws of physics weren't just the way they are, we couldn't be here. The sun couldn't be there. The laws of gravity and nuclear laws, magnetic theory, quantum mechanics, and so on have to be just the way they are for us to be here." So we see this fine-tuning of the laws of nature that allows the universe to be habitable by life. Another famous cosmologist named Fred Hoyle, he was at Cambridge University. He said, "A common sense interpretation of the data suggests that a super intellect has monkeyed with physics as well as with biology." So I would say that IB's prediction has been confirmed. So I'm going to skip this because we are coming around. Well, actually, let's go through it. Let's talk about, very briefly, how did the universe begin? This is going to be our last piece of evidence showing design in nature. Now, for millennia, for centuries, there have been debates between people about whether or not the universe had always existed or whether or not it had a beginning, basically a first cause to get it going. And I would say it was somewhere sort of just before and around the Middle Ages that various Muslim and Christian scholars developed an argument that is called the Kalam cosmological argument. And it's an argument for a first cause for the beginning of the universe. And it goes like this. It says, there's 3 parts to it. It says, number 1, anything that begins to exist has a cause. 2, the universe began to exist. 3, therefore, the universe has a first cause, okay? Now, the problem was that for many centuries, we did not have enough evidence from the world of science to help us to actually confidently address this question of whether or not the universe began to exist. Some people would say the universe had existed forever, that it was eternal in nature, there was no beginning to the universe, and then other people would say, no, the universe did have a beginning, therefore we need a first cause to explain how the universe got going. But finally, in just the last, I would say, 100 years, physics and cosmology has made discoveries which show that the universe did have a beginning. The first major discovery was what we call the redshift of the galaxies, where basically we see that when we look at various galaxies that are out there in outer space, we see that there is a shift towards the red spectrum of light. And this is due to the Doppler effect, and it shows that these galaxies are actually all moving away from us. The implication is that if all these galaxies are moving away from one another, then if you were to sort of rewind, the tape, rewind the motion of these galaxies, you would find that initially everything came from one infinitely dense, infinitely small point in space and time that everything exploded out from, and that has come to be known as the Big Bang. The idea that the universe began with sort of this initial expansion event with this incredibly powerful, infinitely dense, infinitely small point of all the matter and energy in the universe exploding out from this point. Now, that Big Bang model made a very specific prediction, that if it was true, we would find what's called the cosmic background radiation that would be sort of, when you look at the sky, you would find this radiation that's left over from this initial Big Bang event where the universe first got going. And in the 1960s, scientists discovered this precise cosmic background radiation that was predicted by the Big Bang. And then in the 1990s, they sent up a satellite to measure the exact frequencies of this cosmic background radiation. It's in the microwave level. And they basically discovered, to a very precise degree, the exact frequency of radiation that is predicted if the universe really did start off with a bang. So the Coulomb argument now can be settled that yes, the universe did have a beginning. So we can say anything that begins to exist has a cause. The universe began to exist. This is demonstrated by the Big Bang model, strongly supported by the redshift and the discovery of the precisely predicted level of background radiation detected by satellites. Therefore, the universe has a first cause. So the universe basically had a beginning, or a beginner, some kind of a first cause. I would call it a mind that exists outside of space and time. So it's a transcendent being. It's a super powerful creator which created the universe and everything that we see in it. So I think the implications of the Big Bang are really quite profound. So let's go through a summary of some of the scientific evidence for design. Number one, we have the discovery of digital information, biochemical language, and information processing systems of the cell. Number two, we have the discovery of irreducibly complex molecular machines. We find these highly complex machine-like structures that challenge Darwinian evolution, running around performing vital functions inside of our cells. Number three, we have the discovery of the fine-tuning of the laws and concepts of physics. And then number four, we have the discovery of the Big Bang and the evidence for sort of a creation event at the beginning of the universe. So that's my summary, you guys. So thank you very much. Before you come, I want to make one last point. Dr. Miller and I actually have written a free ebook. And for those of you who are interested in this topic, you can click on this QR code here and download this book. It's actually published by a South African academic publisher. And Brian Miller, who you'll hear from in just a few minutes here, he has a fantastic chapter in this book on engineering and biology. I have a chapter on human origins, including fossils, and there's also chapters that go into some of the evidence we just talked about, the evidence from chemistry, physics, and cosmology, and how all of that points to design. And just to give you guys a couple other resources here. These are some great websites and more information. We have evolutionnews.org, which is our daily news site. We have intelligentdesign.org, which is a wonderful sort of gateway to get all kinds of great information about intelligent design. We have a YouTube channel where you can get all kinds of great animations, including animations of some of the molecular machines that I've been talking about today. We also have a podcast, I Am Future Podcast, which comes out on a weekly basis. So lots of great content there. Of course, we're on social media, Facebook, Twitter, and Instagram. And finally, last slide here. If you guys are really interested in this topic and you want to dive deeper into the evidence for intelligent design and you're a student, we have international seminars on intelligent design. Unfortunately for the international students, they're online, but they still are fantastic programs. In fact, a number of folks here who are with Biocosmos have attended our seminars. We had a great time getting to know them and interacting with them. The seminars happen every year in July, so if you're interested in learning more information, go to this website here, www.discovery.org/SEM, and you can apply to attend to next year's program. I think applications won't open up until January, but we would love to have you guys apply to attend. So thank you very much, and I appreciate you guys being here.